Just as Daniel said, welcome to the session. We've got a number of interesting looking presentations today, starting with Nadia Falzoni talking on Monte Carlo evaluation of radionuclides for early brain metastasis targeting. Thank you.
Morning. Thanks for the introduction. So my talk, as they briefly said, is regarding Monte Carlo simulation of brain metastases. We know that brain metastases still presents a significant clinical challenge, and it is estimated that between 10 and 30% of patients with systemic cancer will develop a central nervous system metastases. These are principally originating from three primary cancers, namely lung, breast, and melanoma. And current treatment options include surgery, radiotherapy, which is basically whole brain or stereotactic radiosurgery, or combinations of both with chemotherapy. However, the overall survival remains poor, with 47% of new brain metastases arising 11 to 15 months after initial radiosurgery. In our institute, we are particularly interested in breast cancer and its seeding to the brain. The reason being is that we have robust preclinical mouse models that have confirmed the brain parenchymal infiltration of breast cancer cells. These models have been developed by Professor Nicola Simpson, and as can be seen by this magnetic resonance imaging of early brain metastases seeding of breast cancer cells that have been dosed with MPIO particles. And this occurs as early as 14 days after intracardiac injection. They further identified the role of cellular adhesion molecules, which are basically inflammation markers, and we are exploiting the possible role that VCAM1, which is one of the markers that they've identified for a target for targeted radionuclide therapy. So the aim of this study was basically to develop in silico models to evaluate the efficacy of a range of different alpha, beta, and Auger emitting radionuclides for therapy. The one thing that we need to understand is that if we can look at this immunohistochemistry slide here, VCAM1 is expressed on the endothelial cells. So the blue staining here shows you the breast cancer cells as they are recruited to the site of inflammation, and then they extravasate into the brain parenchyma. Once we then evaluate the different radionuclides, we then choose the two most promising in terms of dose deposition to evaluate the DNA double-strand break yield and RBE using an atomistic model. So briefly, just an overline of the methodology. We use two photon microscopy with a viewing window to evaluate the seeding of the cells to the brain. So the orange is the vessels, and the green is GFP modified breast cancer cells that have seeded to the brain. So again, just to recap, VCAM1 is expressed around the vessel wall. And the idea is then that an antibody-labeled radionuclide would then bind to these sites, and we would then evaluate the dose deposition using a Monte Carlo geometry model where the vessel is simulated as a cylinder, and we look at a disk or volume of interest where we then have our atomistic model. If we look at the data from our animal model, we had to group the vessels into different sizes because of the variation that you see in the microvasculature of mouse brains. So vessels less than 5 microns, 5 to 10, and greater than 10 microns. What we did notice that with all of these, you had a cooperative growth of the cells around the vessel, and the maximum penetration of the cells were up to about 50 micron. They exceeded in lateral in length up to about 100 microns. So from our Monte Carlo simulation then, it was run in liquid water using GN4 processes. We varied the vessel diameter and length, and we assumed that the activity was uniformly distributed on the inside of the vessel. As I've already mentioned, we have this disk that we've identified as our volume of interest. This was specifically chosen to fit our atomistic model, which had a width of 3.5 microns, and it extended the active volume in which we transported the radionuclides up to about 110 micrometer. This was to capture the most energetic alpha particles emitted from our alpha emitting radionuclides. And we selected a cutoff energy of 8 eV, so any electron energy lower than that was deposited locally. Inside this disk, we enabled the DNA processes, and outside of this, it was the Livermore physics processes. The atomistic model can find more data or detail about that in the publication of Bernal, but it basically consists of a cube in which we've got about 6 gigabase pairs of chromatin fibers, which is more or less the same number of gigabase pairs that you would find in a normal human cell. And then these volumes of interests were spaced 5 micrometers radially apart to simulate the position of cells. So if we look at the dose deposition, then and A is the betas and Auger electrons, and alpha in part B. If we look at the dose per decay, we see that terbium presented or gave the highest dose per decay, followed by lutetium. However, if we look at the normalized dose, which is what we are interested in because we want to have more of a uniform dose distribution over that initial 50 micrometers of penetration, the forerunner here was lutetium. Very interesting, though, was that gallium-67, which is a Auger emitter, also had a very nice dose profile. That of yttrium-90 was was very close to that of lutetium, but we chose lutetium as the best candidate for the beta emitters. Then if we look at the alpha emitters, actinium, because of its 4 alphas in the decay scheme, obviously departed the most dose. However, again, following the argument that we wanted a more uniform distribution of dose within our 50 micrometers of penetration that we see for early penetration, and also because we wanted to have an alpha emitter that potentially can penetrate further, we chose lead-212. So if we look at the DNA double-strand DNA strand break yield, then the total dose, the reason why you don't see the black dots is because the electron dose is superimposed on the total dose. So the contribution from lutetium is basically due to the betas. Photon emissions contributed very little to the dose. And the double strand break yield for lutetium was approximately 2.67 double strand breaks per gray gigabase pair. If we, however, look at lead-212, we see these very interesting maxima, and they can only be explained if you look at the decay scheme of lead-212, because lead in itself is not an alpha emitter, but decays to bismuth-212, which 64% of the time decays to polonium, which then decays to stable lead by the emission of almost 9 MeV alpha. And 36% of the time, bismuth decays to thallium-208, which in turn decays to stable lead. So if one projects these ranges of these 2 alphas, the 9 and 6 MeV alphas, their ranges are approximately 50 and 100 microns. But these maxima occur at about 40 to 90 microns. And the reason being is that it's not just a simple superposition of ranges, but these radionuclides are isotropically emitted. So you've got superposition of the different Bragg peaks due to this isotropic emission. Lastly, then, we looked at the RBE. This was in comparison with cobalt-60 as our test radiation, and cobalt-60 produced about 3.6 double-strand breaks per gray gigabase pair. So for lutetium, we see that the RBE is almost, it's less than 1. And compared to lead-212, we again have these maxima, which coincide with the Bragg peaks of the two alphas. And lastly then, the double-strand break per decay gigabase pair. One thing that I must mention is that we change the number of events for lutetium run so that we can have comparable statistics and dose compared to the alphas. So it would seem then that lead would be a potential candidate for targeted radionuclide therapy. And one thing that I want to mention is that it's not always necessary to use preclinical animal models before you start with this kind of preclinical investigation, but it is very helpful to have in silico models to first evaluate a bouquet of different radionuclides to see what is the best candidates that match your geometry and the cancer that you're specifically looking at. And then, as I said, lead is a potential candidate, and also this model can be extended as a predictive indicator of DNA double-strand breaks for specific radionuclides. This work was recently published in Theranostics if you are interested to read up further. And just my thanks to all the people, specifically the contribution of Professor Bernal, who provided the atomistic model, and Professor Ackerman, who helped with the DNA simulations. Thank you very much for your attention.
Has anyone got any questions for Nadia?
With the radioisotope distribution, are you trying to get the radioisotope to attach, or sorry, the radioisotope to treat the cells just close to the vessel? And do the cells in the later stages of the cancer migrate deeper into the brain? And if that's the case, you've got to get it really early.
The idea would be to develop the whole hypothesis being here is that if we can detect cancer at such an early stage, we can treat it. So the idea would be that we will catch it at very, very early stages, and therefore alpha particles would be preferable in this context because of their limited range. But you and I know that the physics is one part that we can sort the biodistribution, and that we can't do anything about.
Are there any other questions? Can I just ask a quick question, completely naive? How difficult is the atomistic model to implement in GANT4? Is it quite well documented, or?
This has been so. Mario developed the atomistic models. My understanding is, well, we had quite a lot of trouble doing the simulations.
Fair enough.
It was not an easy process. I mean, some of these simulations ran for about 2 weeks. So we had that's why we had to curb our, we ran this physics models on the outside of the atomistic model, which was that specific disk that we identified. And if we hadn't done this, the computational time would have been months.
Yes. Sorry.
Question. I wondered if you considered the escape of the radionuclide from the lead.
Yes. Yes, we have a second paper discussing that. Yes, it's a very interesting story because it's not just the recoil daughters, but because of the initial beta emission that you can actually have bismuth coming off completely from the lead-212, which nullifies the whole construct as a targeted radionuclide therapeutic. The thing is that they have a beta chelator, which is TCMC, which forms a cage around the radionuclide, which potentially makes it more stable. But we are in the process of investigating this because we have seen previously, that physics and chemistry don't tally up. You think something is stable, but actually, it falls apart. So we are busy investigating that. Thank you. That is a very important point.
All right, thanks, Nadia. That's very interesting. I'd like to ask Matthew Griffiths to come up for the next talk. It's entitled Salt Activation to Assess Neutron Flux as a Proxy for Radiation Damage in a Cyclotron Vault. Thanks, Matthew.
Well, going from the microscopic to the macroscopic, this is a project we've been sort of working around quietly for some time, and I put it in here more out of general interest, and I didn't expect to get a presentation, but nonetheless, hopefully you'll find it rather interesting as well. So, at Royal Brisbane Hospital, we've got a GE cyclotron, which we make fairly large amounts of FDG for distribution, and in nuclear medicine, diagnostic, even therapeutic, we very rarely see direct and real-time macroscopic effects of radiation, but for distribution centres, we start to see this environment because we're running at just quite a different activity level. So the first one that caught me by surprise was at somewhere activities around about over 500 gigabecquerels per in a vial. We start to see the FDGs start to effervesce, or the positrons are tearing through the water and breaking down the water into hydrogen and hydrogen peroxide. So you start to see bubbles in the liquid, and that shocked me. So you actually, one of the tests for a pharmaceutical, it's got to be clear and colourless. You look at it the first time, it's clear and colourless. You go back and look at it a few minutes later, it's cloudy. You think, what have we done? So it's actually real-time, direct, see it with your eye effect with radiation. Chemistry modules, program logic controllers can just fail after several years, mainly due to the gamma exposure from the excess radioactivity left in the waste, which is about 40% of, well, between 40 and 60% in the hot cells. Around a cyclotron, if the cyclotron's not self-shielded, it's in a room, you get neutron activation of non-cyclotron parts. We have got a collection of emergency lighting batteries, which are too radioactive to throw out, helium cooling pumps, air conditioning motors. There's a variety of bits and pieces that are going on. So again, this is a real world, measured with a Geiger counter, and also solid state electronics fail in the cyclotron vault within the order of months. Now, we've got several devices in the cyclotron. Proximity sensors on some waste gas tanks. The cyclotron vault's a nice shielded environment, so any waste gas from the chemistry modules gets stored in the tanks, and the sensors on them fail on a regular basis. A radiation detector we've got sitting in the cyclotron vault has failed due to detecting too much radiation. So we wish to investigate whether it was possible to protect the electronics in the cyclotron vault, mainly because we've got some new equipment coming. And it's probably going to be in the same location, and likewise we've got sick and tired of replacing vaults. Now, again, I'm sure you guys all understand this, but the cyclotron is a negative ion cyclotron that accelerates protons, and they smack into O18 and produce the PN reaction. That's the source of most of our neutrons, and that we turn into F18, then FTG, and you know all the rest of the story. So, and with adding a CT, it looks much better. Okay, so coming back to the neutrons, when you have up to an 18 MeV proton coming in, it carries a lot of forward momentum. So generally speaking, the neutrons leave the target fairly fast, as far as they are as an energetic state. And likewise, due to conservation of momentum, they tend to be forward scattered at about a 30-degree cone. So the neutrons are flying off more or less in the same direction as the proton beam. They then scatter all over the place. At this early stage, it's elastic scattering, so the neutron bangs into a nucleus and then ricochets around the place, slowing down. I like to tell visitors the cyclotron vault, we just sweep the neutrons up at the end of the day, but that's not quite the case. So eventually they become thermalized, and this is the second stage, where they will interact with wherever they happen to be, whether it's in the cyclotron vault, it's in the battery, they're going to go all over the place. So this stage is effectively a neutron gas, and producing some reaction, which is going to be most likely an N-gamma reaction, which will then probably decay, giving up beta particles, Auger electrons, or potentially gamma rays and or alpha particles. So you get other reactions as well. So it's a real mixed environment in the cyclotron. You don't know what was going on until you actually go and measure it. So cyclotron dose rate volts, or dose rates in volts, for those who don't run cyclotrons, we have the GE PET trace, and it's often a dual target run, so you've got basically 130 microamps of protons, and if you remember the number of protons in an amp, that's huge. So running for 90 minutes, and we'll produce up to 700 gigabecquerels of F18 in the cyclotron. So for every F18 atom, there's a neutron. There are some people in this room who produce gigabecquerel runs every day. So the gamma dose, mainly from prompt gamma reactions in the nucleus, so you've got neutrons and protons interacting in isotopes producing the gamma rays. And the dose rate in the cyclotron vault, which is a room you can walk into when the cyclotron's running, is in sieverts per hour. There's no precursor. Neutron dose, mainly from the O18-PN reaction, but anywhere else the beam interacts in solid materials, there's a chance for other PN reactions. So anywhere there's a stray beam, you wind up with additional neutrons. So the radiation dose in that environment is tens of sieverts per hour. So the dose rates are again, they're at a different level. They're radiotherapy type environments. Okay, we understand generally gamma radiation attenuation, but we don't didn't have a practical hand on neutron attenuation, and we suspected that the neutrons, probably the fast neutrons, are doing most of the damage to the electronics. Clearly, the fact that the chemistry modules die, there's no proton, no positron interaction, it's just gamma ray. So eventually the gamma ray dose will kill the electronics, but we were suspecting much faster damage in the cyclotron. So if you're interested in this, there's a nice little paper or PhD thesis that's available on CERN, which covers radiation damage in a gamma and a neutron detecting environment, which is what we're looking for. So gamma radiation in solid state electronics is mainly the creation of, if you like, extra charge carriers as the electrons become free inside this piece of solid state, leading to increased conduction and eventually some physical damage. Fast neutrons. Now, those fast neutrons, when they have elastic recoil with the nucleus as they're slowing down, dump enough energy in the atom for it to bounce out of its lattice plate. So the recoil energy is greater than the chemical binding energy of the substrate. So they tend to lead to multiple displaced atoms. In fact, some of the secondary events also create holes, if you like, or create new spaces in the lattice where the nucleus has knocked out. Most of this has not come from my understanding, it's come from reading this paper. So if you're interested, have a bit of a read. So they're effectively, from our point of view, they're quite high LET atoms. They were the atoms originally in the piece of solid state electronics. So creating additional hole pair, electron hole pairs, and eventually you get disruption and destruction of the conduction band. And what's even more amusing, the more recent the transistor, the narrower the conduction band, the more likely it is to be susceptible to a single point damage because the conduction bands get so small. Older transistors, strange enough, are actually more reliable because they're just physically bigger and you have to destroy more atoms to have a piece of electronics fail. Thermal neutrons. Again, by this stage, neutrons starting to be absorbed by the atom, and what's going to happen is that that process doesn't produce much energy, but when it decays, if it decays, you could get Auger electrons, beta particles, alpha particles, again, local damage. But the highly energetic environment is in the fast neutrons. Okay, so we thought, well, we have a neutron monitor. It's a purchased gamma neutron monitor. If you read the specifications, it's looking very good. For the neutron side of things, a full energy range, thermal, intermediate, high energy neutrons, it's looking good. High sensitivity, it's got very good gamma rejection up to 6 MeV, that's looking good. Nice cyclotron environment. You can measure the gamma radiation dose from 50 keV to 6 MeV, that's looking all right. Up to 10 sieverts, that's our ballpark. So we put it in the cyclotron volt for one run. The neutron measurements seemed sensible, the gamma dose didn't return to zero. So basically the monitor had become radioactive. So it did save some time having to find a check source to make sure the thing was working, but it didn't really make it much use as a gamma monitor. It did return, fortunately the half-lives were fairly short, so it did return to normal operation after a while. So basically you've got to find another approach. So you can't just go out and get a bit of electronics to measure the damage to the electronics. Makes sense. Okay, oops, where are we? We had previously looked at the paper by Fujibuchi, and it was done in 2009, and it was their idea to use salt. They were looking to find a method of absolute quantitation of the neutron flux in a cyclotron volt. It's a detailed paper, it's nicely written, but we are implementing it on a far more, if you like, rudimentary or empirical process. So basically, if you take standard salt, sodium chloride, and put it in a cyclotron volt, salt is it's made of sodium, which is 100% sodium-23. Undergoing an N-gamma reaction makes sodium-24. When the emissions from sodium-24 are a beta particle, fairly high intensity, and 2 gamma rays. And again, for nuclear medicine, it's a little outside our comfort zone, 1.3 MeV and a 2.75 MeV gamma ray, 99% of the time. And the half-life's 14.9 hours. And that decays into stable magnesium. So again, cyclotrons do alchemy. We're turning salt into magnesium, but we're getting a kick out of the gamma rays in the meantime. Chlorine comes in 2 flavors, naturally. Chlorine 35, and again, an N-gamma reaction takes it in chlorine 36, a nice beta ray coming out of it, but the half-life's 3 by 10 to the 5 years. So from a nuclear medicine perspective, that's stable. I don't care. So we're not going to worry about that from here on in, and it turns into argon. Likewise, the chlorine 37 turns into chlorine 38, and again, a couple of betas and a couple of reasonable gammas, actually surprisingly similar energies, 1.6 MeV and 2.17 MeV. And this is the useful bit, the half-life's comparatively short. So one's a useful thing to measure over a day time period, the other one decays away as you watch it. So you can actually put the salt in the cyclotron run and get 2 different isotopes, one of which will decay away and one of which won't. So we had previously looked at this simple masters project, and again, very empirically, we just got them to put a drum of water and some borax actually in the drum to see if we can look at the neutron reduction. And that was a nice little project, but here we're trying to do something a little bit different. So we basically got 2 grams of salt, literally went to the kitchen and got some non-iodized salt and poured it into the thing, weighed them out carefully in the plastic counting tubes. They were exposed to 1 run. That's 1 run in the morning. Then indicated from about 4 hours, again with the relative half-lives. The amount of chlorine-38 is less than 0.2% of the total count flux, that should be fine. And we put it on an auto gamma counter because I'm too lazy to sit there and count them manually. And they run for 10 minutes, and using just an open window. It could be isotope specific, but we're pretty certain, I'll explain why in a minute, only the counts are coming from the sources that we're looking for. We then take that count rate and, again, for consistency, repairing across runs, normalise it back to the end of the cyclotron run, and likewise normalise by the mass of the salt and the total beam current, which is effectively how many neutrons it was exposed to. Again, very empirical. We're just comparing counts with counts. Before we did all that, we actually did go back and ensure that the count data we were getting was linear with the cyclotron. Short run, smaller counts; longer run, more counts, 1 target; less counts and 2 targets. So we got something that looks like it's performing fairly well as an empirical measurement. If you throw it in the auto gamma counter, this is what you're seeing. This is your energy spectrum. So sure enough, you've got a 1.37 MeV gamma ray from the sodium, the 1.6 MeV from the chlorine. This is 2 hours post-irradiation. And again, given that the chlorine is only relatively small abundance compared to 100% abundance, and it's a relatively small proportion of decay path, that's kind of what you expect. These are characteristics of the counting system, so I'm not going to worry about that. And obviously the 2.75 MeV gamma rays is beyond the scope of our system. It did cause some complication with backgrounds, so we had to separate the sample so that the gamma ray didn't punch through the lead on the counter. We did, out of curiosity, throw it onto a high energy or high resolution system, and sure enough we see our sodium gamma ray as expected. We don't see the sodium high energies, off scale. We saw 511, it's nuclear medicine, there's patients around. Yeah, okay, it's unfortunate, a bit of penetration. Couldn't explain this peak until we sat down and did the mathematics and said, for the sodium, you've got pair production going on for the 2.75 MeV gamma ray. So you've got the 511 is not from our nuclear medicine patients, it's 511 from the pair production inside the detector, and the additional peak, which was causing us to scratch our heads, was actually the residual energy. So again, this is stuff we generally don't see in nuclear medicine, which took us a little while to tumble the idea. Okay, again, just to confirm that what's going on is what we expect, we put a sample that was a fairly, quote, hot sample on the auto gamma counter, just let it go round and round and round and round. Yeah, obviously what looks like a bi-exponential curve. You do the curve stripping on it, and you get a 15.09 half-life for the long one, 14.9 for sodium. I'm pretty sure we got sodium there. And again, the lower count was a bit noisier because of the smaller count rates, but we got a 31-minute half-life, chlorine 38, should have a 37-minute half-life. I'm pretty certain that's all we've got going on, so I'm pretty much confident this is what's happening. Okay, for thermal neutron shielding, we went out and bought some borated plastic from a commercial company, and we were expecting, and the marketing blurb says that the hydrogen in the polyethylene obviously will slow down some of the neutrons, and once they become thermalized, the boron has a much larger cross-section capture, so it should start to catch the neutrons and slow them down, looking for protection. So we manufactured a box, wall and lid thicknesses of 20 millimeters with an overlap, so there's no line of sight anywhere. And basically we put the samples inside the box and put the box in various locations around the cyclotron, and very complicated sticky tape some salt on the outside. So there's my background, there's my sample. I'm doing this entirely empirically. I'm not going to try and quantitate the neutron flux. Okay, so this is a panorama, so the geometry is a little bit distorted. So the cyclotron sits here and the beam fires more or less directly at this environment. These are our storage tanks. There's a sensor up here and a sensor down there. And if you walk around the corner and walk past the back of, got the back to the cyclotron, there's a radiation monitor sitting up on this wall here. And we've destroyed this 4 or 5 times, and we've destroyed these numerous times. Everything else in the room is pretty radiation insensitive. So there are our sensitive monitoring points. So we basically took our little box, and again, you can do 1 sample per run, or 1 per day, or if you're doing 2 runs a day and you're prepared to dive in and out of the cyclotron when it's warm, not hot, you can do more than 1 sample a day. And we basically got the boronated box was reducing the count rates between background and normal by a factor of 3.4 to 5.3. So if we could delay our detector replacement time by a factor of 5, that was a bit of a win. These are repeatable results, and that distribution and ratios is just the nature of the cyclotron in the particular room it's in. As the electronics always provided the mount, we did the same test with the lid off the box. So if you imagine the box sitting over the detector, or the box sitting over the radiation sensitive bit of gear. And then what happens if you only shield it in 5 sides? The reduction factor is reduced by, from 3.4 to 2.7 and from 5.3 to 3.7. So it's not as effective, but still you're getting a bit of a win. We're also curious. Sorry? Okay. We're also really curious to find out it was just a polyethylene, and we just put a polyethylene block in the place, and that was done. We also stuck a salt sample up the concrete tube, and that provided a factor of 9 reduction in the induced activity. So it did really well. Fast neutrons. Sodium is effectively thermalized. We have a Ludlam sphere monitor. We tore it apart and took the detector out. If you've never seen the inside of one of these things, it's a big ball with a polyethylene sphere, some aluminium to some beam hardening, and the detector sits in the middle. We just swapped the salt samples for that, and again, we could now do measurements of higher activities and lower activities. So effectively, what we're expecting to see now is the opposite. We're expecting to see more counts in the bonosphere than outside, because you've got now reducing the fast neutrons down to a thermal environment and measure them. So, and again, we saw the greatest increases in counts in the salt compared to the background when the bonosphere was in the forward scatter area. So activation of the cyclotron can be used to empirically determine thermal neutron flux. You can use this to look at assessment of reductions of thermal flux, and the use of bonospheres allow you to extend the approach into higher energies. So to shield electronics from neutron damage, it's suggested what you should do, and again, this is a fairly standard process for high energy particles. Put it inside a bonosphere, and inside the bonosphere you should have some boron-aided capture that would do the job. It's all very interesting, but in reality, we've just been better off spending our time getting longer wires and different sensors. So it was an interesting and worthwhile experiment, but in actual fact, get the detectors out of the cyclotron vault. Thank you.
Thanks, Matthew. I'm afraid we don't have any time for any questions, maybe on purpose, Matthew.
Cool. Thank you, Steve.
That's good.
Right, our next presentation is by Boon Lee, who will be talking on Monte Carlo evaluation of different targeting strategies for Auger electron-emitting medical radionuclides.
Good morning. So I would like to talk about our work on Monte evaluation for Auger electron-emitting medical radionuclide. In this case, we use indium 111 in 3D cellular models. So it has been suggested that short-range Auger electrons can be ideal for targeting micrometastasis because the range is short, so it will cause minimal damage to nearby healthy cells. There have been several Monte Carlo studies being published. They explore whether the Auger dose is good enough to elicit tumor residual effect in small clusters, small cell clusters. However, all these Monte Carlo simulation, they don't actually link their simulation with experimental observation in order to predict the efficacy of Auger electron emitters. So in this study, we look at the Indian label radio constructs. In this case, it's an Indian DTPA, human epidermal growth factor, that targets the EGF receptor, and Indian DTPA trastuzumab that targets the HER2 receptors. In this study, we look at the 2D monolayer and 3D spheroid models. And we use the survival fractions and tumor control probability as our biological endpoints in the study. So here in the top panel, you can see that the spheroid model we grew in the lab for 3 different cell lines. MDA, MB468, and 231H2N are the human breast cancer cell line, and for SQ20B is a head and neck cancer squamous carcinoma cell line. And all these spheroids, they are about 400 to 500 micrometer in diameter. And the bottom panel shows the confocal microscopy images of EGFR expression. And for MDA, MB468, and SQ20B, there is a high expression of EGFR. So you can see the green color here. And for the blue are the DAPI stained nucleus. In the figure F, you can see there is very minimal EGFR expression, but we can use the Indian trastuzumab to target 231H2N cell lines. So based on the confocal microscopy images, we can determine the cell and nuclear radius. And here, for example, is the MDA MB468 cell line. There is a clear correlation between the two quantities. So we use the correlation and fit it into a event-driven dynamic algorithm. We build out our in silico computer models for the 3D as well as the monolayer, but here we only show the I only show the 3D spherical model. And so next we want to know where exactly are the indium located when we incubate the spheroid with the aforementioned radio constructs. So for indium EGF, we found that after 24 hours, MDA MB468 spheroid exhibit pretty much uniform radionuclide radioactivity distribution. For SQ20B, which is EGFR positive cell line, you can see here that the radioactivity is pretty much located on the surface of the spheroid. And if you look at these figures here, the SQ20B cells form a very tightly packed, a tiny rim around the spheroid, blocking the diffusion for the radio construct to get into the center. And for HER2 positive cell line, 231H2N, treated with trastuzumab for 24 hours, you can see that similarly to the MDA MB468 in this case, it exhibits uniform radionuclide distribution. So from these micro audioradiograms, and we can know that there are two possible radionuclide distribution, uniform or peripheral. And based on this distribution, we perform Monte Carlo simulation to determine the S values so that we want to calculate the dose. And we perform the simulation separately for nucleus, cytoplasm, and cell membrane to get these three quantities. And after that, we calculate the dose based on the Merck formalism, which utilize the S values, as well as we derive the cumulative activity from the internalization data for each cell compartments. So here we look at the crossfire effect contribution to the total dose. For sources in the nucleus, pretty much that due to the short range of Auger electrons, there is very minimal crossfire effect from one cell to another. For sources on the cell surface, because it's much closer to, it's very close to another cell, so it contributes significantly to the dose in another nucleus. And another interesting feature you can see from this figure is that as we move away from the center of the spheroid, the crossfire effect decreases. This is because cells on the peripheral region of the spheroid usually have less surrounding cells, so you receive, the crossfire effect diminishes as you move away from the center of the spheroid. So to test our model, we first perform clonogenic assay experiments for monolayers. Here shows the summary of what we found for in vitro experiments. The first row shows the experimental survival fraction that we have derived. And the second row shows the calculated survival fraction based on linear quadratic models. In linear quadratic model, we need three quantities, dose, and alpha and beta values. So for the alpha beta values for each cell line, we determine it using cesium irradiation. And these values are shown here. The dose was calculated, as I mentioned before, using the Merck formalism. And as you can see, if you compare the first row to the second row, for cells treated for 24 hours, the theory consistently overestimates the survival fraction. Then we know that Auger electron can cause dense ionization around the decay sites. And there has been suggestion or evidence that when the nucleus-bound Auger emitting radionuclides could actually impose a much higher biological effectiveness. So in the second iteration of our modeling, we said that, all right, RB equals to 4 based on this published paper for nucleus-bound indium-111. And what we found is that after adjusted for this effect, we bring the theory in a much better agreement with the experiment, apart from 231H2N after 24 hours. And the reason is that if you look at the alpha beta values for 231H2N, the beta value is 0.06 compared to 0.12 of the alpha values. So for this cell line, the alpha to beta values ratio is quite low. So it makes this cell line to be resistant to dose protraction effect. So, I mean, resistant to delivery of a protracted dose, which is in this case in the most of the targeted radionuclide therapy. So in the next iteration of the modeling, we included the dose protraction effect into the linear quadratic model. And then now we bring the survival fraction up to be in agreement with the experiment. The increase in survival mainly due to the fact that when 231H2N are allowed to repair during the protracted dose delivery. So we can get agreement after the third iteration. And the next thing is that once we have got agreement for monolayers, we wanted to look at the spheroids tumor control probability. In this case, we didn't manage to do experiment. Unfortunately, when we peeled the cells apart from the spheroid, they all died, so we couldn't get experimental data for spheroids. But in this case, we assume two different radionuclide distribution. One is uniform for 468 and peripheral for SQ20B. As you can see that for the uniform distribution, radionuclide distribution, most of the cells receive quite a huge amount of dose, and we can certainly control this kind of micrometastasis using Auger electrons. And for SQ20B, because it just cannot, the radioconstruct cannot penetrate into the core, it's just pointless to use short-range Auger electrons. So in conclusion, enhanced RBE may come into play when Auger electron-emitting radionuclide are in the nucleus, and at least that is what we found in order to get an agreement with the experiments. And of the three cell lines that we look at, only MDA and MB468 spheroids can be controlled using short-range Auger electrons. So it means that in order to utilize Auger electrons in treating micrometastasis, first you have to look at what is the morphology of that particular cell lines, and also depends on the radiosensitivity of the cell line. So in conclusion, it is essential to include biological endpoints such as survival fraction and tumor control probability when evaluating the distribution of radionuclides in micrometastasis models. Thank you. And here I would like to thank all the collaborators and as well as my colleagues, especially Dr. Nadia Falzoni, who proposed the project. Thank you.
2 minutes for questions. Yeah. Has anyone got any quick questions for who?
You found that dose prolongation factor was important, but did you model the change in the dose deposition pattern as you moved from 0 to 24 hours for the radionuclide that started on the surface and ended up uniformly distributed?
Because right after 1 hour, pretty much is they are uniformly. We only look at for two different cases. For MDA468, we assume pretty much uniformly distributed throughout the 24 hours. So we didn't model the change in from peripheral to not peripheral, because it's not really peripheral. It's just not fully uniform. For the MDA468 after 1 hour incubation. Is that what you're asking? Okay.
Is there any other questions? Oh, thank you very much, Wayne.
Thank you.
Okay, so our last speaker for this session is Graham O'Keefe. He's going to be talking about ghost calibrated modelling with GANT4, and because the session actually ends at 12:30 and this is the last talk, so Graham, you can keep going for a few minutes longer as you wanted to, I believe.
Okay,
Thanks, Graham.
we'll try not to. Okay, so dose calibrated modelling. What's motivated this particular study is variations that we've been seeing in standard uptake value for our gallium traces. So standard uptake value is a critical semi-quantitative metric for measuring change in metabolism in PET imaging. And the simplified expression for it there is you've got, voxel activity concentration divided by what would have been the uniform activity concentration if the injected activity had been uniformly distributed throughout the body. So a key to this then is having an accurate representation then of the injected activity. So the bottom part of that expression there, the denominator, is going to be dose calibrated or related, and the numerator term, the voxel activity concentration, that's on the scanner side of things. So we're looking at what's going on in the dose calibrator side of things. So as I said, the motivation for this was that we were seeing differences in SUV between our standard F18 compounds and our gallium-68. So what you can see here then is that mouse not working, right? Mouse not working. So what you can see is that the F18 SUV, that's the graph to the left, that's sitting around about a mean of about 1.03, so it's about 3% higher. Whereas the gallium-68 SUV, we're getting that sitting at about 0.95. So there's an 8% difference. So we wanted to know what was going on there. So the sources of bias that we can possibly have, as I pointed out, the activity reconstruction side of things is the numerator term, and the dose calibrator is then on that denominator term. So where is that 8% difference coming from? Well, on the reconstruction side, the first thing that comes to note is that the gallium-68 branching ratio, if we look at it there, 88.9%, it's about 8% lower than the fluorine-18 branching ratio. So the first question you have to ask is it in the reconstruction side? Is it in that numerator part? So we investigated that by, first of all, acquiring our usual gallium-68 uniform phantom, and then looking at the abundance factor as it's referred to in the list mode header, and we modified that to change it to half the value, reconstructed, and it did the right thing. So we knew then that the branching ratio terms in the reconstruction process were being correctly handled, because that wasn't at all clear at the time. So that then takes us then to start looking at the dose calibrator, the denominator side of things. Now, what does the dose calibrator do? It's converting ionisation current into number of decays per second. So there's a number of factors that have to be taken into account there. How much energy is there per decay? What is the branching ratio for decay? And so forth. What types of particles are involved in decay? Gammas, positrons, electrons, and so forth. And they're all encapsulated within this one magic term called the gain or the dial setting. So for the Cap&Tech series, it's called the gain setting. For the Atom Labs type dose calibrators, it's called the dial setting. And they account for that chamber efficiency and the branching ratio effects. We calibrate our dose calibrators annually with a standard NIST source. We'll see shortly, that's sort of a question of its own. And the values that we ended up using for our dose calibrators, for germanium/gallium, we've got a dial setting or a gain setting of 448, and for fluorine-18, 480. Now, it's worth noting that in the initial manufacturer recommendations for gallium-68, germanium-68, that dial setting was actually around 418, so it's really low. So we decided at that point that we wanted to be able to do some sort of modelling of these various ranges of isotopes so that we could get some sort of feel for what those gain settings should be, because we weren't really we don't always have access to a range of NIST sources. The only one we have in this case here is cesium-137 and germanium-68, for example. There is no practical F18 standard. Now, if we look at it purely from an energy deposition point of view, you can see that you can go through that and you can sum up all your main photons and so forth. You end up getting per decay, for example, for gallium-68, 948 keV per decay. And you compare that to what you get from fluorine-18 decay, sum up all those, it's 989 keV per decay. So even from an energetics perspective, we should have had a ratio of gallium-68 to fluorine-18 of about 0.96. And we compare that to what our dose calibrator settings are, which is 442, sorry I don't have a mouse, but 442 divided by 480, 0.92. So even the modified settings we had are lower than the purely from an energetics point of view, not taking into any account, and that's assuming your uniform dose calibrator response. So taking no account of varying energy response of the dose calibrator. And as we'll see shortly, the Giant 4 simulations, they were giving us a ratio of about 0.9855, 0.99. So let's go into that. So this was what motivated us then for that modelling. We don't have a practical fluorinating standard. There's a whole range of isotopes that aren't supported. In fact, with the current range, so with the original range of dose calibrators, Captain Tech had this huge list of isotopes. There's 60, 80 isotopes in there that were all referenced back to NIST standards. Strangely, when they released their PET series, their 25 PET series, their 55, there's 3 isotopes in there. So they've stepped right way back from that and basically put it back onto the user to make sure they validate their own calibrations. So we want to model that, and Giant 4 is the natural tool to use for something like that. So that involves constructing the dose calibrator, going through and making a range of sensitive detector definitions, putting in the production physics for radioactive decay, transport physics, all the standard things that one does within Giant. So there's a schematic representation of the dose calibrator. That was sort of determined somewhat from a mass calorimetry point of view because Cap and Tech really weren't that helpful, so I had to pull apart an old dose calibrator and actually work out what was inside it. So those levels there, you can see we've got it made up of a series of Teflon, concentric cylindrical components, the lead, which is on the outside of the shielding. Again, I don't have my mouse. And you can see, does the laser work? Because someone tried that first. No, I'm not going to bother. Oh, there is a laser. Okay, and so you can see there the lead component, the inner Teflon component, the aluminium component. All right. So, and that's what. Yep. This is on a funny angle. So that's what a basic modelling output would give you from Giant. It's not great in this, but you can see here's the positron decay coming out from, in this case, fluorine-18. So it's all been absorbed within that Perspex inner sleeve. And of course, the photons that are coming off from the annihilation are getting into the gas component of itself. So at that point there, what we're doing is the standard sort of thing. We're doing energy scoring, we're counting up the energy, and we're working out how much energy we're going to get per decay. So it took a while. So I went through and did a range of 20 isotopes. Also looked at a range of monoenergetic positron sources and monoenergetic gamma sources, so I could characterise the electron-positron response and also the gamma response. And a range of geometries, so point source, syringe source, adding in the chamber, adding in the Perspex insert, adding in the external shielding. So the types of results we got from that, here's the actual, so going through with those monoenergetic photons, we got that type of response there. When I first did that, I actually put steel in by mistake because I didn't know what the actual ionisation chamber wall was made of, and it just zipped down here and didn't look anything like what I knew it should look like. And here's the positron or the electron response that's been modelled from that as well. And that's there is the measured response that Cap and Tech have come up with. So that made me reasonably happy to see something like that. There are some differences in the response around this region here, and that probably is going to have a major effect on some of the lower energy isotopes we'll see shortly. There's the beta or the electron response. So here's a range of beta spectrum for a range of isotopes, and when you scale these by that previous electron response that I showed you, you'll end up getting a resultant type of response like so. So for gallium-68, you can see that if you don't have any shielding, if it's a point source, no inner Perspex shielding, you're getting a huge response coming off from the beta pluses. By the time you actually start putting in your Perspex layer and so forth, you've attenuated all of that response. And we see that here when we model these pure beta emitters. If we look at yttrium-90, for example, with a point source, we're going to get about 600 electron volts per decay, which is quite high when we compare that to fluorine-18, where the photon response is sitting around about 1300 electron volts per decay. So this would be a significant component if it weren't shielded out. Once you put the syringe in and then the Perspex insert, you've basically knocked out all the betas as you expect. Phosphorus-32, similar sort of story. So the end result then is that after all that modelling, we can look at the electron volts per decay versus the gain setting for the detector, and we get a reasonably nice linear response. Most of our 511 sit around here. These two aren't behaving themselves. That one there, it's very low energy, so the low energy response probably isn't perfectly modelled. The I124, there's a lot of, they're very high energy beta pluses, so we're probably not correctly modelling the beta plus mechanism at this point. So they're unknowns at the moment which need more work. And where are we? So just a little sort of sidestep. Of course, having done all of this, we then finally dug up a paper from 2015, or the end of 2015, where NIST had come out and modified their F18 NIST standard. And the essence of that is that the 480 gain setting that you saw before for F18, you have to reduce that down to 460. So we did that. We went through and decided at the beginning of the year, we recalibrated all our PEC cameras for F18 to 460. And we put in place so we've adjusted our dose calibrators. We then put in place a series of, this actually went back 18 months, but 3 months before that modification, then about 3 months after. So you can see the clear step there in germanium-68. F18 is staying roughly constant, as you hope. Gallium-68 is not so clear. It's quite a noisy measurement compared to the germanium-68. This germanium-68 is a uniform source, so it doesn't go in the dose calibrator. And so it's a reproducible measurement over 2 years. Whereas this one's got phantom preparation variables in it and also dose calibrator uncertainties. So this is somewhat more of a noisy measurement compared to that. But it doesn't really, and we can see here that change. We've introduced a 6 to 7% increase for germanium-68 compared to what it was prior to. So it's had obviously the required effect, and F18 hasn't changed much. Something funny is going on with gallium-68 still, but like I said, it is a noisy measurement, and you certainly can't do a single point measurement with gallium and expect to have calibrated your system. There we are. So, yeah, sorry. So, in conclusion then, I think I've just gone through. Oh yeah, I was highlighting just to show through some of these things, these ratios here. So yeah, the story's not finished with gallium-68. We're still about, we end up still being about 5% low compared to fluorine-18. But that's somewhat better than the 15 to 20% low that we would have been if we'd been using the recommended settings. So there's future work to do. We've still got this issue of why is germanium-68, it can't be different from gallium-68, but something's going on. We suspect that it's related to generators, because depending on what species you have, when the gallium-68, I've been using it out of the generator straight as an AU and then putting it in phantom. Where you get a gallium trichloride complex coming out of that, it's non-soluble, so you've got to be careful how you actually prepare that. Best way to prepare is to actually go through a synthesis process. It's difficult for me to get time from chemists to actually do that, but maybe I'll have to become a chemist, I'm not sure. Differences in gallium-68 were observed when we changed generators, and again, that's touching back on that. I'd like to look at extending the monitoring program to other cameras, because it's only been on Philips cameras today. So that's the future work I have in place for this. Thank you. And we're in time for lunch. There you go.
Yeah, plenty of time for lunch. Are there any questions?
Yeah?
I mean, it's just a mess. It's
It is, yeah.
so variable with respect to syringe and vial.
Mm.
It's something like this. We're using iodine 124 to try and characterize iodine 131 dose rate. So variations in one are going to be therapeutic variations in the other. So we're a little concerned.
The geometry's huge. I mean, you do your P32 measurements, you know that straight away. So.
But at the same time, I'm wondering if there's possibility of looking at like a band hardening effect or a copper shell to knock out all the positons and try and clean that up. Have you modelling that?
Look, the Sloan Kettering people have been through a similar process, and so they have that same recommendation, putting in it's only something like a tenth of a mil of copper as a sleeve inside the dose calibrator. So yeah, we should be looking at that.
I would like to add, like, we might catch up on.
Yeah, yeah, sure.
Just one comment.
Yeah.
On the, when talking about SUV, on the reconstruction side
Yes.
of it, there is a known problem of the so-called prompt gamma correction. There's only 3.2% of this, is it 1,000 something kV gamma line with the gallium-68. In some applications of gallium-68, we have a very, very hot bladder. In these cases, you would see like a halo around the bladder, almost negative values there, because you subtract too much scatter. Even if you don't see it, there is a slight deduction of the activity. And these this prompt gamma correction is handled differently by different vendors.
Yeah, yeah, you're right. I mean, and that's even more of a problem with I-124. So all of these dirty isotopes have that issue. Sure. Yeah.
In the Siemens camera, there is a way of modifying that. It's recommended by the Siemens system. There is a way of addressing that to improve it. Recently, I was messing around with that dose calibrators for an entirely different reason. I was 3D printing some dose calibrator inserts, and I was want to double check that I got the same answers. And I found as much as a 2 to 3 degree difference in angulation of the syringe gave me a 4 or 5% difference in the result. So it's
What was the source?
Fluorine and gallium.
Fluorine.
So it's much more sensitive to position in the dose calibrator than we all think. I actually went back and reprinted or recreated a syringe hanger so the syringe couldn't sit under slightly skew angle. I'll show you some later if you like. But much more sensitive than we
Yeah,
expect.
look, I discovered a lot of that accidentally when I was building the J-out models anyway, because getting the geometry right and debugging all of that, I came up with some interesting geometries. And yeah, it's a very sensitive effect.
They're
Yeah.
much more lengthy bit of equipment than we'd like them to.
Yeah.
Any other questions? All right. So I will just remind you that at 12:30, but they're probably setting up now-ish. Lunch is available, according to my notes here, on the ground level foyer. And also, you're reminded to sign the wall of friendship, whatever that is and wherever it is.
Can I just ask all the presenters, just want to say thank you very much to the great presentations. Could the presenters just hang around for a couple of minutes afterwards, just in case anyone's got any questions? I don't want to hold you back from lunch, but and thank you all very much for coming, and thank you very much to the presenters for their presentations today.